grateful to open this online mini school on stochastic semi-groups of random operators. We are truly honored to have with us Professor Andrei Dorogovtsev from the Institute of Mathematics of the National Academy of Science of Ukraine. Professor Dorogovtsev is a corresponding member of the NIS of Ukraine, head of the Department of Stochastic Processes, and a leading figure in the field of probability theory. He has also been actively involved in numerous international collaborations and serves on the editorial boards of several prestigious journals. Over the coming days, Professor Dorogovtsev will deliver a series of lectures covering a wide range of topics, from strong random operators in Hilbert space to stochastic follows and semi-groups. We encourage you to take full advantage of this opportunity to learn from an expert and to engage in discussions. Once again, I would like to thank Professor Dorogovtsev for sharing his expertise and all of you for your participation. Let us make this mini school a productive and inspiring experience for everyone. So thank Professor and I now hand over to you for your first lecture.
Okay. Thank you very much for such a kind introduction. And really, I am pleasured and it is a big honor for me to give a series of lectures in Jilin School of Mathematics. Thanks, Professor Han, for the kind invitation. I want to present in these lectures some, in my opinion, interesting subjects, like mentioned stochastic semigroups and random linear operators in Hilbert space. This subject arise in many various branches of modern stochastic theory, stochastic process theory. I kindly ask all participants, don't hesitate to ask questions during my lectures, or if you will be interested in the continuation of discussion of such subject, please write mails to me and we can continue such discussion. Now let me start my demonstration on the screen and we will start our lecture. So here is my screen, and let me I'll find a board. Okay.
Yeah.
Let me take it. So today we will discuss how random stochastic apparatus appears and what is stochastic semigroup. Let us start from the most distributed example of the semigroup. Simple example. Consider RD and some matrix A here. So A is a square matrix. Consider a linear differential equation, which is very familiar to everybody. dxt axt dt. Then one can write the solution to Cauchy problem for such equation if x0 is equal to u as follows. Xt is equal to exponent of AT U. So we have here such an expression, and it can be defined easily using the exponent series for exponent. So exponent A t is equal to sum from 10 equal to 0 to infinity. Here is a in power n, t in power n divided by n factorial. It can be easily checked that the sum converges to matrix. And what is interesting, if we denote this matrix by t, indexed by t, it occurs that we have an interesting property. T plus s is equal to t superposition of ts for t and s, which is greater or equal than 0. So we see that this family of operators inherits some good properties relatively to addition of numbers on the real line. Always when we face such good properties, it is worth to understand how to use it more deeply. So people began to think that began to call such family by the semigroup, uh, and try to use it. Of course, the simplest using is to connect it with the initial differential equation. For example, if we want to consider more difficult but also familiar to you equation like dyt equal uh, a yt dt plus some influence from outside ft dt. Then it can be shown very easily that the solution to Cauchy problem for this equation looks like the following formula. We have yt equal to t indexed by t from u plus the integral from 0 to t t indexed by t minus s fs ds. So we can see that this semigroup, this family of operators, can be useful at least in the solution of a different linear differential equation. And moreover, those of you who are familiar with the theory of differential equation knows that asymptotic properties of the solutions are determined by the eigenvalues of the matrix A or its Jordan decomposition. And here people mentioned a very interesting fact. We just define dt as an exponent, but it can be proved. It can be proved that if the family of matrices are semigroup. Of course, we need some technical conditions. I will I will formulate a precise statement later. But it occurs then This family is represented as, as an exponent of some operator A. This operator A is called is called by a generator of the semigroup, and formally can be defined as follows. This is a limit of tt minus identity divided by t. We have seen that in very simple case of a linear differential equation in Euclid space arise interesting object, and this object is uniquely defined by the some matrix A. We have a simple and effective way to discuss linear differential equations. Since then, we can try to apply this to more complicated pictures. Let us try to do this. And much more complicated example is related to partial differential equation. Equations. Let us consider as an example a well-known heat equation. Here we have the equation for a function, so we have to write partial derivatives. Let me discuss the one of the simplest but well-known and very important equation like this. Here is Laplace operator with respect to partial arguments, and again we have a initial condition for Cauchy problem that u from x t0 is equal some function, for example, phi of x. Everybody again know from the simple course of partial differential equations that this heat equation under good condition on function phi has unique solution, which is to Cauchy problem for Cauchy problem, which can be written as a convolution with the Gaussian kernel. So we know that u x t is equal to the convolution phi with pt from x, where this pt is a density of Gaussian distribution. I will denote this density by usual notation 0 u, because in different dimensions we have different expression for this density. So, for example, when we have a dimension d equal to 1, pt of x is equal to 1 over square root of 2 pi t e minus x square 2 over t. And when dimension is greater than 1, then pt has a form 1 square root of 2 pi t in power d, and here is e minus norm of x square divided by 2t. It can be checked that if we denote Such convolution, which define our solution as tt of f of phi. So this is a phi convolution with p t. Then again we have the same semigroup property. We have that Ts plus T is equal to composition of Tt Ts. By the way, now it is not so easy to check it. We have to calculate some integrals, and usually some students say, oh, it's boring stuff to make these calculations. But here there is a very interesting connection to probability theory, firstly notices by the Mark Katz and Kolmogorov in the middle of previous century. And let me recall you that we have a very nice property for Gaussian random variables. Namely, if we have a sum of two independent Gaussian random variables, it again became to be a Gaussian random variable. So the convolution of Gaussian densities is again Gaussian density. And due to this relation to Gaussian distribution, one can see that here we can use some notion and object from stochastics. But before we will do this, I just want to know, to mention that comparatively to the simple case of a linear differential equation in the finite dimensional Euclid space, here we don't have so simple conclusions about asymptotic behavior. Even one can relate again the semigroup TT heat semigroup can be related to Laplace operator, which we have in the right part of our equation. You remember. But still, the formula 1/2 of Laplace is equal to the limit when t tends to 0 plus tt minus identity divided by t now must be justified. And we have to understand what is written there, because we understand that this is a formula related to some connections between operators in some functional space. We already have a feeling that functional spaces are infinitely dimensional, Hilbert or Banach, or moreover topological spaces, where it's not too easy to work with operators. For example, one can have no eigenvalues, one can have a so-called continuous spectrum. We will study it. By the way, it is exactly our case when we consider Laplace operator on the whole space. So it is not too easy to say, okay, this operator has eigenvalues which is negative, so our solution goes to zero exponentially fast. No, we have not such very easy conclusions. We have to study operators in infinitely dimensional space. We have to study convergence of such operators in different sense. And for those of you who already studied functional analysis, I have to say that Laplace operator is not bounded operator in space, for example, continuous function with uniform norm, or square integrate function on all space. So we have to understand how to work with unbounded operator, and we see that when study a semigroups in a more general case, we must have a well-developed heavy machinery for this. And now you can imagine how difficult object we will study in these lectures, because we will study stochastic semigroup. So, moreover, it will be not only unbounded operators, it will be not only convergence on some operators in Hilbert or Banach space, but it will be also random objects. Now, let us recall the connections which I mentioned to stochastic for this heat equation, which was mentioned by Kolmogorov, Markats, and this connection is closely related to the notion of Wiener process, or process of Brownian motion. Sometimes it is called Brownian motion. There are a lot of different ways to introduce this very rich and very useful, very interesting mathematical object. I will use just simplest for us way. Mainly, I will consider firstly a dimension equal to 1 and use the following definition. Random process Wt, t is greater or equal than 1, than 0, is called by Wiener process if the following condition holds. The first one, W is Gaussian process. It means that all finite dimensional distribution of W are Gaussian distributions. Second, W of 0 is equal to 0. Third, we know that a Gaussian process is uniquely determined by its second moments. So to fix the distribution of the Gaussian process, we only need to fix two functions. The first function is its mean, and I will suppose that its mean is equal to 0. And the next function is its covariance. And I will suppose that the covariance, namely the expectation of Wt Ws, has a form a minimum Ts. Sometimes in the future, to avoid long formula, I will denote it by T, this angle S. It occurs that this minimum Ts is positive definite function, so one can consider such a random process, and this random process has a lot of good properties, namely, W has continuous trajectories. It is not trivial. But one can check this using Kolmogorov condition, sufficient condition for random process to have continuous trajectories. This is not a subject of our lecture, so I am not giving you the proof of this statement, but you can check textbooks about Kolmogorov condition of continuity of random process and try to apply it to this case. What is important for us right now that W has stationary independent increments. Like we have the following property. If we consider Wt plus S minus Wt, it has the same distribution as Ws, and it can be checked that this is a normal distribution with zero mean and variances. For any Ts, which is greater or equal than 0. When I said for S equal to 0 normal distribution with the variance S, it means that the distribution is concentrated in its mean. So this is stationarity property. All increments have the same distribution, which depends only on the length of the interval where we take this increment. And second property is the following: if we consider subsequent moments of the time, like t1, which is greater or equal than 0, less than t2, and so on, less than tn, then the random variables wt2 minus wt1 and so on, wtn minus wtn minus 1 has are independent. Actually, these properties follows easily from our willing to have a mathematical description of particle which randomly moves in isotropic and stationary random media. So our particle moves due to the interaction with the molecules of the media. Then it is expected that the trajectory of the particles will be continuous. It cannot jump outside of the media. Also, since we say that conditions are stationary, it is expected that statistical characteristics of increments does not change with the time. And since the speed of molecules of the media usually is much bigger than the speed of the particle, it interacts with different molecules in different moments of the time. This leads to the independence of the increment. So we have a natural conditions. But as we already said, Wt has a normal distribution with the parameters 0 and t. So we have a very nice formula, which is a partial case of Feynman-Cast formula. We will use it in all of generality in the future. But our solution to heat equation can be represented as follows. This is expectation of the function phi from x plus w. You see? So one can think that the solution to heat equation with the initial value phi can be express it in terms of Brownian particles, which start from the point X where we want to have the solution. Yeah? This is a very helpful. This is a very helpful representation for initial heat semigroup. You remember that we already define operators T, T, and this is T phi of X. Yes, this is a representation of heat semigroup. And using this representation, one can try to achieve some asymptotic properties of the solution. And it is true that we can get such the results in such way. But to go further, to consider a much more interesting example, we just need some at least small understanding about integration with respect to Wiener process. What I mean, we already have seen integration. With respect to Wiener process. We already have seen that Wiener process has a lot of good properties. Let me mention it again. We need it. W has continuous trajectories. W has stationary and independent increments. But unfortunately, if we will study its structure just more deeply, we will get some bad surprises. For example, W has non-differentiable trajectories. And unfortunately, this non-smoothness is very deep. For example, one can prove the statement that W with probability 1 has trajectories which has no derivative at any point of the interval, for example, 0, 1. From this point of view, one can ask how we can integrate with respect to W, because I said it a few minutes before. Answer is one can try to do this in L2 sense, in sense of convergence in square mean. Main property here is the following. One can have a very simple statement. Let me denote it by lemma, but I am not going to check it. It is easy, and you can check it by your own. That if we have the increasing partitions of the interval, for example, 0 to t and equal to t, then the following relation holds. Such sums from k equals 0 to n minus 1. Here is w tk plus 1 minus wtk square is going in two sense to t when the maximum of the differences between our tk plus 1 minus tk goes to 0. Please check this. It is very easy using the uh, properties of the Wiener process, which we mentioned, and properties of Gaussian distribution. From the point of view of this lemma, one can get very interesting conclusions. Let me formulate these conclusions in not rigorous but very useful way. One can say that dwt square is equal to dt. You see, it looks like ridiculous from the first point of view. I consider some differential that does not exist for Wiener process, but when we look for this onto this formula, one can understand what I mean. If we accumulate a lot of small increments of w in square, we get the expected value. So we have such a nice relation. And from this point of view, one can define, one can make two interesting conclusions. First one is the Ito stochastic integral. Ito stochastic integral. Let us consider some function f, which is an element of L2 0, 1. Then, due to this relation, one can obtain a good integral, for example, from 0 to 1, fs dws in L2 sense. I am not going to consider all details of the construction, but due to this relation which we mentioned, it can be seen that when we use the approximation of f by the step functions, then we can get a limit of the integrals from step functions, and this limit will be a good random variable. By the way, it is Gaussian random variable, and moreover, it has the following parameters. It will be useful in the future: 0 and integral from 0 to 1 ft square dt. Moreover, one can build, it was done in different ways in works of Ito and Gichmann and Skorohod. One can build the stochastic integral with respect to W, not only for deterministic functions f, but also for functions which are random but connected or measurable with respect to W in special way. Again, this is at least now, this is not our business how to uh, mm, how to do all technical details here. All what we need to know is that one can define a good stochastic integral with respect to Wiener process. This is the first conclusion. Second conclusion also is very interesting, namely Ito formula. Ito formula. Let us consider some function f, which is smooth with respect to both coordinates and depends on wt and t. One can, as usual, try to find the differential of this superposition. You remember, in real analysis, we said that if we take some smooth function from the smooth function, then we have the following form. Then we have some good formula for changing of the differentials. Here we also have a good formula. It occurs that we have the following formula, namely, it is equal f prime, the first derivative with respect to the first argument, t dwt. This comes from this is expected. Yes, despite of we have some new construction of the integral. Here is Ito integral. Ito integral. We still have feelings that maybe it must be in such form because this is the first differential. Why not? Plus the differential related to the derivative with respect to the second argument. It is also expected. Yes. F prime 2 here is wt t dt, and we have some initial term. Why this term is appears? The reason is this, that we still have something which we obtain from Taylor expansion, which give us dt. So this formula shows us that relatively to the first argument, we have to consider Taylor expansion not only up to the first order derivatives, but for the second order derivative. And we do this, and we get 1/2 because of Taylor expansion f2 prime with respect to the first argument wt t dt again. Now you see this, by the way, you see this 1/2, and let me connect it to heat equation. Maybe when I wrote heat equation, here, some of you say, why he wrote this 1/2? Why we just don't write Laplace operator? This is a reason. This is a connection to Wiener process, connection to Ito formula. Of course, we can discuss just scaling Wiener process. We can discuss heat equation with arbitrary argument, arbitrary positive argument before Laplace operator. But I insist that this 1/2 is exactly related to Ito formula for differential of smooth function from the Wiener process, and we have exactly this nice new formula. But from this point of view, one can understand that maybe since we have already expressions, differential expressions, which contains the derivatives. You see, here is a second derivative of the function, first derivative, and the stochastic integral. One can expect that maybe people already discuss a lot stochastic partial differential equation. It is true. Stochastic partial differential equations. Let us consider an example of such stochastic differential equation. I will write here differentials. Du equal, for example, 1/2 of Laplace of u dt plus. Let me consider here uh, the scalar product of radiant of u multiplying some vector a, and here is dwt. Of course, one can add here some terms of the first order related to non-stochastic integral, but we discussed just example, so let's continue. And Cauchy condition u x0 is equal to phi of x. Now, one can think how to study this equation, how to study the properties of solution, even how to prove that the solution exists. And what we expect? We again can expect that again will exist the family TT of operators. For example, if one of the natural space is L2, is a family of operators in L2 RD, such that we have representation uxt is equal to tt of phi of x, such that tt plus s must be equal to some superposition of tt ts, and maybe it must be related to some generator, to some operator A, and so on. So we also want to have such representation of the family of the solution to Cauchy problem, and we again want to have this semigroup property, but it is understandable now that t greater or equal than 0 is a stochastic semigroup. Stochastic. Its elements are random. Stochastic semigroup. So we just see the reasoning. Why we have to pay attention to families of what? Of random operators which organize for us semigroup. Because at least one, but a strong reason is that using this notion, one can expect to study a stochastic partial differential equation, which is related to, for example, like this equation which we see, which is related to heat expansion in the random media, and so one can imagine that stochastic partial differential equation arise naturally. We have to study such equations. One of the possible way is to look at the semigroups of operators for representation to solution of Cauchy problem, and it occurs that now the elements of the semigroup are random, and we have to study random operators. Random operators. I will discuss mostly operators in Hilbert space. We have seen L2RD. Further, we will consider Sobolev spaces and so on. But it occurs that in Hilbert space it is much more easy to do this in Hilbert space. Maybe you already have feeling that Hilbert space inherits a lot of properties of finite dimensional Euclid spaces, and we have a very well developed theory of linear operators in this space. So let us begin. I will think that H is a real separable Hilbert space. The question is, what is a random operator in H? And I insist that this equation is not too easy as it looks like. Because usually when we discuss something random, for example, from the course of probability theory, you remember, take a random number from 1 to 2000. Discuss its number theory properties. Or take a random point in the square 0, 1 square, yeah, and so on. And one can imagine that this is a natural and usual way. When we say take something random, we have to do the following. Namely, just take the whole set of this object. In our case, we can start from this one. Let us take LH is a set of all bounded linear operators in H. Then randomize this set. So take a distribution. Consider a probability distribution. On H. And now we get a problem. Because those of you who carefully study course on probability theory knows that when we want to discuss some probability measure on the space, in our case, space of all linear bounded operators in H, we have to discuss the sigma field. Sigma field of subsets of LH. And usually, when we have a space with good metric structure, this is our case, because in LH we have operator norm. We usually say, okay, let us consider Borel sigma field. And now we face a problem. Why? Because if dimension of h is equal to infinity, one can imagine very easy infinite dimensional Hilbert space and understand that we need it. For example, here we mention this L2 space on RD. It is already infinitely dimensional. You must remember from functional analysis L2 small space, and you must remember from quantum physics that we describe the position of the systems or particles in quantum physics by wave functions, and these wave functions are element of complex Hilbert space, and this Hilbert space is evidently infinitely dimensional. So this is a very common situation. But in this very common situation, the space of maybe of bounded linear operators, the space LH is not separable. Is not separable. Please check it. Not separable. Then the Borel sigma field is not countably generated. From the first look of view, it looks like, oh, it's some formal property. We don't need to discuss this property when we want to do some really good job and application and so on. But it is not true. When you discuss the measures on the non-countably generated sigma field, you face a lot of problems. For example, you cannot say that measures is almost concentrated on the compact and, and so on. So it is a very bad equation, even very bad property, even from the point of view of applications. Yeah? So we can proceed now in two different ways to overcome this difficulty. One is, let us specify the operator which we need. For example, one can say, okay, let us consider a random projection over some basis, fixed basis. Then, of course, you will have a good subset of LH, and you can consider probability measures on this subset and so on. This is the first way. Another way is much more intriguing. One can try to think not about the operators, because at least from the point of view of applications, we don't need to study deeply maybe the structure of the operator itself. We want to understand how it is acting on the element of the space. So the idea is the following. Consider not a random operator itself, not a random operator itself, but its action on the elements of H. H. So we do not need operator A. We need A of H for H belongs to H capital. And it occurs that in this case, one can get nice objects which are subjects of our consideration in the next lectures. For today, that's all. Thank you for your attention. And let me summarize what we did today. Today, we considered the sources of the random semigroup theory. Namely, we understood that for solution to linear differential equation in a finite dimensional space, we have a good representation related to deterministic semigroup of operators or matrices. We understood that this deterministic semigroup is uniquely defined by the one operator, which is a limit, which is appropriate limit or derivative of our semigroup. We understood that more or less the same, but with more technical troubles, can be done in case if we consider linear differential equation now in functional space. We understood that such semigroup which arise there can have probabilistic representation, which is based on the Wiener process, and basing on the integration with respect to Wiener process, one can get a very nice, representation to the solution of heat equation, for example, and one can build stochastic partial differential equation. In this ways, stochastic semigroup arise. And to study stochastic semigroups, we need to study the notion of random operator in Hilbert space. And we began to do this. And next lecture, tomorrow, we will study random operators and its properties, its integral representations in Hilbert space. For today, that's all. Thank you for your attention. If somebody have questions or comments, please.
So, any question? Thank you, Professor. Thank you very much. Yeah.